Greetings and welcome to the Chemistry 221 Valence Bond and Molecular Orbitals Lab. And in this lab, we're going to compare the two main models used to explain why molecules form. Like, you have to think about it. There's no reason really why atoms need to go into molecules per se, but they do, which is good for us because most of our body is made up of different kinds of molecules. So DNA, sugar, caffeine, things like that all have a lot of jazz going on. So we're trying to explain here like why molecules come together. And we're going to look at the two theories, and both of these theories more often than not overlap really well. So the results are the same, but there's quite a bit of differences between them. Valence bond is a theory that you can do literally anywhere. They call it a back of the envelope calculation. It's something that you can do pretty easily without computers, looking at Google, something like that, pretty chill. On the other hand, molecular orbital theory is very complicated, and it goes back to the atomic orbitals, which was based on Heisenberg's and Schrodinger's work in the quantum chemistry realm we talked about in Chem 221. On the other hand, molecular orbital theory gives much more information than valence bond theory does. So if you do have access to a supercomputer or something like that, molecular orbital theory is the way to go. I always tell my students that one day I hope that you'll all have the TI 2000 calculator or the iPhone 1 million or whatever, right? And you'll just be able to boop, 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 put in some information, and out will come this molecular orbital information, and score, I won't talk about valence bond anymore. However, we're still a ways away from it because MO is pretty complicated stuff. So anyway, let's look more about what this lab has to offer, and we'll look at the differences and similarities between valence bond and molecular orbital theory. In this lab, again, you're going to compare the two main theories, valence bond, which of course I'll abbreviate VB, and molecular orbital theory, which I'll abbreviate MO. All right. Valence bond is really just another extension of the Lewis structures and the Vesper geometry stuff we looked at in the last lab. So valence bond goes along really well with them, which is pretty chill. On the other hand, molecular orbital theory is an extension of the atomic orbitals we talked about in Chem 221. So when we went through all the quantum numbers to get to things like 1s2, 2s2, 2p2 for hydrogen, those are the kind of things we're going to use to make molecular orbitals. It's a much more mathematical system. There is math in valence bond too, but nothing compared to molecular orbital theory. MO is pretty crazy. Again, valence bond, pretty easy to apply, but it certainly isn't sophisticated as MO. And in this lab, we'll look at several examples where MO is better than valence bond. On the other hand, we don't use molecular orbital just every day because it's very, very difficult. You usually need not just a regular computer, but a supercomputer, stuff like that, to make things happen. So if you have the resources to make a molecular orbital analysis, absolutely go down that path. On the other hand, if you don't, and it's just a few institutions that can do this kind of stuff, then valence bond works really well. So they are nice complements. There's a couple of handouts which are going to be really useful. The geometry and polarity guide, which we used in the Lewis structures lab, you will definitely be using that in this area too. It's in the companion, it's on the Chem 222 website, and you can also download it directly using that link there, mhchem.org/GOPO for geometry and polarity. All right. In addition to that though, you're also going to need the molecular orbital diagrams, and there's two of them. One of them is for boron, carbon, and nitrogen, and the other one is for oxygen, fluorine, and neon. These are also in the companion, and they are online on our website, or you can download them directly from mhchem.org/mo. They will help us when we get to the molecular orbital theory information. So valence bond theory is pretty easy to apply. And again, it's an extension of the Lewis structure Vesper stuff we've done. So if you need to apply valence bond theory, first thing you want to do, draw the Lewis structure. All right, no problem. From that, you can apply the Vesper rules. So for example, in last lab, we saw that CH4 was tetrahedral for both electron pair geometry and molecular geometry, 109-degree angles, nonpolar, stuff like like that. That's what you'll do too when it comes to valence bond. But the new part now is that the electron pair geometry will also tell you what's called the hybridization of the central atom in the Lewis structure. So in the little molecule there of methane, CH4, in the lower right-hand corner, CH4 is in a tetrahedral electron pair geometry. Every time you see a tetrahedral name, you want to say it's sp3 hybridized. In the lecture for this section, I talked about where that came from. Tetrahedral is the result, in carbon's case, of 1 2s orbital and 3 2p orbitals. They hybridize or mix together, and there become 4 orbitals of the same energy. All right, they're called hybrid orbitals. So when you see sp3, you know 2 things. First of all, it came from 1s and 3p orbitals. That's cool. And the second thing is that there's going to be 4 hybrid orbitals around that central atom. So around carbon here, using my green pen, you could have like 1 orbital there to that hydrogen, a second one right there to that hydrogen, a third one, and a fourth one. The central atom is hybridized. The outside atoms just use their atomic orbitals. So in the CH4 molecule right there, the hydrogens are all using their 1s1 orbitals. And s orbitals are kind of spheres, so that s kind of smashes into one of the sp3 hybrid orbitals, and the interface then between them, that's where the sigma bond forms. So hybridization, when all is said and done, comes down to a term, and those are the 5 possibilities there: sp, sp2, sp3, sp3d, or sp3d2. And you'll use the electron pair geometry to assign one of those 5 types. So every time you have a tetrahedral central atom, you will call it sp3 hybridized. Every time you have an octahedral electron pair geometry, the hybridization of the central atom will be referred to as sp3d2, stuff like that. And honestly, that's all there is. It's very mellow. Where they get the terms and how the bonds come together, that can be a little bit crazier, definitely. But the important part is that to list the hybridization, it's literally just one of those 5 kinds. And you look at the electron pair geometry to do that, no problem. Again, valence bond is pretty chill. In molecular orbital theory, you end up with pictures like the one for N2 in the lower left-hand corner. And I want to talk about how we built this structure in the first place. First of all, we're only going to look at diatomic molecules. So diatomic means 2 atom molecules. So we will look at N2 and O2 and C2 and F2, stuff like that. But we won't do something like CH4 we saw on the last slide there. CH4 has 5 atoms. That's a little bit beyond where we can go with molecular orbital theory at this level. In addition to only talking about diatomics, we're only going to talk about diatomics up to neon. So we're not going to talk about like chlorine, all right? We're not going to talk about sulfur, phosphorus, arsenic, stuff like that. This will keep our discussion a little simpler, and later on, if you do look at this more, you can then use all our ideas and extend it out. When you're drawing a molecular orbital diagram, there is an atom on the left and an atom on the right. Now this example is for nitrogen, N2. Nitrogen is a 1s2, 2s2, 2p3 configuration. So here's the 1s2, and there's an up and a down arrow because that's Hund's rule, kind of only pair them up when there's no more room. Right above it, higher energy, is the 2s2, and then right here is 2p3. And notice again that each electron is in its own orbital. Again, that's Hund's rule. You keep them apart and you only start pairing them, i.e. put an up with a down, when there's no more room. So we would say that the nitrogen atom on the left has odd electrons. It's paramagnetic. Now, in molecular orbital theory, the left side, that's one nitrogen atom. atom. And on the right side, you have a second nitrogen atom. So notice that there's another 1s2, 2s2, 2p3 on that side as well. So in an MO diagram, in a complete MO diagram, there's two atoms, an atom on the left and an atom on the right. In the middle of those two lines I drew, that's where the molecular orbitals come together. So everything in the middle of those two lines, all of those things are molecular orbitals. Notice how there are some 1s interactions right there, and here below between the two lines, those are 2s interactions. So when you're thinking of MO, you can literally have the 1s's and the 1s's coming together. You can have the 2s and the 2s. You can have the 2p's and the 2p's, etc., etc. And that makes it a little bit easier to figure out how this stuff works. When atomic orbitals make molecular orbitals, two atomic orbitals make two molecular orbitals. So you can see down there for 1s, all right, one of the molecular orbitals was lower in energy. It went down relative to the atomic ones, and the other one went up in energy. So the one that's lower in energy, we refer to that as a bonding molecular orbital. So the lower 1s molecular orbital, that's called a sigma 1s bonding orbital. And the other one, the one that went up in energy, that's considered an anti-bonding molecular orbital. So that higher one there, if you look carefully, it's got a little star next to it. The star means anti-bonding, higher energy. So as you fill in electrons, just like we did with 1s and then 2s and then 2p, you just want to take the total electrons and fill them in the middle. So you can see that for 1s, there's 2 atomic electrons on the left and 2 on the right, and those 2 of them go down to the lower bonding and 2 to the upper anti-bonding. To keep the first law of thermodynamics happy, you can't create or destroy any energy. So the lower molecular orbital will be just as much low as the upper anti-bonding molecular orbital will be high. Like you're not losing or gaining anything, like you're taking it away from one and adding it to the other. What that means is that if you have a filled bonding and anti-bonding, like you have in 1s, no interactions. There's no bonds happening in the 1s area. 2s, right above it, is the same way. You've got 2s2 on the left side and another 2s2 for the second nitrogen atom on the right side. Those 2 atomic orbitals will make the lower bonding sigma 2s orbital and the higher anti-bonding sigma star 2s orbital. But again, 2 plus 2, 4 atomic electrons, 2 in the bonding sigma 2s and 2 in the anti-bonding sigma 2s, they all cancel out. So really everything below here is not having any interactions. All the bonding is being canceled by anti-bonding. The interesting part for this molecule is the top part where the 2 p's come together. And notice in this diagram, the molecular orbitals, there's a total of 6 molecular orbitals. There are the 2 pi 2p orbitals, and then there's the sigma 2p. Then right now they're empty. Those are the pi stars and 1 sigma star. So notice it goes like 2 1 2 1, and that's what I called it in the lecture, a 2 1 2 1. This is the so-called molecular orbital for the NBC. Anytime you have N2, B2, or C2, you want to use this 2 1 2 1 kind of configuration. But the important part for right now is that 6 atomic orbitals went in, 3 on the left, 3 on the right, and you end up making 6 molecular orbitals in the middle. 3 of them are lower in bonding, or lower in energy, so those are the bonding orbitals, and 3 of them are higher in energy. Those are the anti-bonding orbitals. So when you take the 6 electrons in this area and you start with the lowest and work your way up, both pi's are filled and the sigma is filled. All of the anti-bondings are empty. So this is the molecular orbital diagram for N2. It's the part in the middle. All right, it's not the other parts like all the way around. It's one thing to build a molecular orbital, but it would be nice to know if the molecule is stable, like can it be made? And that's a really good question. So in molecular orbital theory, bond order is used to tell if a molecule should form or not. And bond order is equal to 1/2 times, parentheses, the number of bonding electrons minus the number of anti-bonding electrons. So in this molecule, I'm going to circle in red the bonding molecular orbital electrons. There's 2 in the sigma 1s, there's 2 in the sigma 2s, and all 6 of these are bonding electrons in the 2p interaction. So if you count up every up and down arrow in that stuff I've circled, that's a total of 10 electrons. Now, the anti-bondings, I'll use blue here, the anti-bonding sigma 1s is right there, the anti-bonding sigma 2s is right there, and here are the anti-bonding 2p interactions, and they're all empty. So you can see in the blue areas then there's a total of 4 electrons, 4 up and down arrows. So 10 minus 4 is 6, and half of that bond order for this molecule is 3. And that's good. If your bond order is greater than 0, it means the molecule should exist. It's stable. Nitrogen is definitely a stable molecule. It's around you right now. So that's pretty cool. You can also check for magnetism. The nitrogen atoms by themselves have odd electrons, like arrows that are up without a corresponding down. So the nitrogen atom, we would say, is paramagnetic. Paramagnetic things are more attracted to magnetic fields than diamagnetic things. The molecule N2, which again is this part in the middle here, the molecule N2 though, every up has a down arrow. So we would say that N2 is diamagnetic. It's not attracted to magnetic fields. The individual atoms are, but the molecule itself is not. Finally, if you had different bond orders, you can actually compare bond lengths. And I won't do that a lot right now, but as bond order goes up, the bond length goes down. So if you had like a bond order 3 and a bond order 2, you would say that the smallest bond order would be the largest length, and the biggest bond order would be the smallest length. You can also use bond energy. Bond order goes up, bond energy goes up. Pretty chill. In lecture, we talked about how bond order, as it goes up, the bond energy goes up, but the bond length goes down. Length is opposite the other two. So this is another thing that you can do, and you can get experience with it in the problem set and stuff like that to see what's happening. I'd like to now draw a molecular orbital from scratch, and I'm going to do nitrogen monoxide, NO. Now, my drawings are usually pretty cheesy, so I apologize in advance, but I really want you to see how this works. NO, I don't remember if it's in your lab or not. I probably should have checked that as the instructor making this video. Whoops. Anyway, doesn't matter. NO is a molecule, so we'll figure this out. If you want to draw nitrogen monoxide, first of all, on the bottom here, you're going to have a nitrogen atom on the left, an oxygen atom on the right, and in the middle, you're going to have nitrogen monoxide, the molecule. Now, as we saw for the N2 molecule earlier, nitrogen, the atom, is 1s2, so I'll have my cheesy 1s line and have an up and a down arrow. Then there's a 2s2, so that's pretty good for this thing. And then finally, nitrogen is a 2p3. Go back to your notes in Chem 221 if that's not certain, or email me if this is unclear. But nitrogen would have a 2p3. You'd have 1, 2, 3 electrons. Remember, the total electrons equals the atomic number if it's a neutral atom, and this one's definitely neutral, so no problem. For oxygen, oxygen has 1 more electron than nitrogen. It has 8 total electrons. So oxygen would have a 1s2, just like nitrogen. It would have a 2s2, just like the nitrogen will. But when it comes to the 2p up here, it's going to have 1, 2, 3, 4. It's got 4 electrons, so it's going to have a paired one there in the 2p. So these, what I've drawn so far, are the atomic electron configurations for nitrogen and oxygen. When nitrogen and oxygen come together, we have a little bit of a dilemma because nitrogen is part of the so-called NBC molecular orbitals, and oxygen is part of the FONE. The phone molecular orbitals I talked about in lecture. I know I need to grow up. But anyway, the question is, which one do you use? And usually the OFNE will trump the NBC version. So what we're going to use in this molecular orbital diagram, we're going to use that FONE. It'll look a little bit different than the N2 molecular diagram we went through in the last slide. So when you're using the FONE, the phone one, the first part is the same. You'll have a sigma 1s and a sigma star 1s anti-bonding. And again, the anti-bonding is a little higher than the bonding, and you can put little things in like that if you'd like to. You can look, by the way, at the FONE diagram, the molecular orbital diagram, and you can see a better picture of what I'm doing here. 2s looks very similar. There's going to be a lower sigma 2s and a higher sigma star 2s. And again, sometimes people use little lines like that to show like where the molecular orbitals came from. Now, this is where the quote-unquote exciting part comes from. In the FONE, it's different from the NBC. NBC had the 2 pi's first and then sigma. Well, the FONE, the sigma is first. They call it sigma 2p. Then you have the pi 2p. And then you have the anti-bonding pi star 2p. And finally, the anti-bonding sigma star 2p. And again, these all came from here, so if you want, you can put little dots and stuff. Yeah, I probably have a little OCD. What can I say? Anyway, this is then the rough molecular orbital diagram for NO, okay? And again, number of atomic orbitals equals number of molecular orbitals. So both nitrogen and oxygen had a total of 5 orbitals, 1 1s, 1 2s, and 3 2p. They each had that, so there's 10 atomic orbitals total. And in the middle, there's a total of 10 molecular orbitals. Woohoo! All right, now comes the fun part where you put the electrons in, and you literally just start at the bottom and move your way up. So 1s and 1s on the bottom, that's 4 electrons. The first 2 electrons go in sigma 1s, the next 2 electrons, sigma star 2s. That fills up both of those, so now we can move on to the 2s interactions. But again, it looks a lot like 1s. So 2s2, 2s2, 4 electrons total. So 1, 2, 3, 4. All right, not a big deal. Again, 2s is filled up just like 1s, so that's cool. But here comes kind of, well, a little bit more fun part. And you know, I can imagine I'm really fun to hang out with parties because I find molecular orbital diagrams to be fun. But anyway, Prophet, back on. Nitrogen has 3 2p electrons, 3 arrows. Oxygen, on the other hand, on the other side, has 4 arrows, 4 electrons. So in the middle part here, there's going to be a total of 7 electrons. So the first 2 electrons, sigma 2p, that's 1, 2. Then I put 3 and 4, and notice I drew them 1 in each orbital. That's Hund's rule. You put 1 electron per room until they have to pair up, kind of thing. Anyway, that's 4 electrons total. We got 7 total to go, so 3 more to go. 5 and 6, we'll pair that up. And finally, 7 will go right there. So the green electrons there show where they go in the molecular orbital diagram for NO. Woohoo! What can we do with this, Russell? Good question, whoever asked that random student in the back of the room. There's a lot of interesting things you can do with the molecular orbital once you have it. The first thing that people usually do is they want to talk about bond order. And bond order is just 1/2 times bonding electrons minus anti-bonding electrons. So in this structure, you had 2 1s bonding, 2 sigma 2s bonding, and 6 2p bonding. So you had 10 bonding electrons total, okay? And from that, you subtract the anti-bonding electrons. There are 2 sigma star 1s anti-bonding, there's 2 sigma star 2s anti-bonding, and there's even 1 pi star 2p at the very top up there. So 10 minus 5, all right? This bond order, 2.5, all right? If the bond order is larger than 0, then it means it's stable. So NO is a stable molecule. But notice it's a fraction. Molecular orbital theory is a lot cooler when it comes to making partial bonds, like half bonds and stuff like that. So this is actually a half bond between nitrogen and oxygen, which is pretty cool. You can think about it as like 1 electron out of 2 in one of the pi interactions, but I digress. You can talk about the magnetism. Now, because of the single electron in the anti-bonding molecular orbital right there, that makes this molecule paramagnetic, all right? NO is a paramagnetic molecule. If they're, like on the N2 example we saw earlier, every up had a down, so that was diamagnetic. Paramagnetic things are more attracted to magnetic fields, which makes them really a little bit more reactive. There's more things you can do with that. You can find a number of sigma bonds. Now, sigma bonds, the definition for finding number of sigma bonds is, again, you take 1/2 the bonding electrons in sigma bonds, and you subtract the anti-bonding electron sigma electrons. So if you look at this, all right, the sigmas, there's sigma 1s, there's sigma 2s, and there is a sigma 2p. So those are the 6 bonding sigma electrons. And anti-bonding here, well, you've got 2 in the sigma star 1s, you've got 2 in the sigma star 2s, but the sigma star 2p, the very top one up there, is empty. So there's 4 anti-bonding sigma electrons. Notice I haven't done anything with the pi electrons, all right? The pi's, the 2 and 2 in the middle of the top part of the molecular orbital diagram, those are, we're going to talk about those in a little bit. But anyway, 1/2 6 minus 4, this is going to be a bond order of 1. So that means because it's sigma, this would be 1 sigma bond. And that's kind of a cool thing. You can do the same kind of process for number of pi bonds. Number of pi bonds, 1/2 the bonding electrons in pi minus the anti-bonding electrons in pi. So we're only going to focus now on these top ones up here. All right, we're only going to focus on the pi 2p, the bonding ones, and the 1 pi star anti-bonding. So for this molecule then, it would be 1/2 the bonding electrons that are pi, or 4, the 4 on the bottom, minus the 1, which is the anti-bonding up there. 4 minus 1, 3, 3 divided by 2, 1.5 pi bonds, all right? Now, if you're ever uncertain about your number of sigma and pi's, here's a really cool and helpful way to check yourself. The overall bond order equals number of sigma plus number of pi. So you can see up here on the top, we had a bond order of 2.5. If we've done this right, our sigma bonds and our pi bonds should equal 2.5. And so we had up here the 1 sigma. We have 1.5 pi right there. Lo and behold, 2.5 equals 1 plus 1.5. Oh, this is a good structure. Remember, bond order equals sigma plus pi. That works not only for molecular orbital diagrams, but Lewis structures as well. If you have a triple bond, 3 bond order of 3, that equals 1 sigma plus 2 pi. So this is a nice kind of way to check yourself. Okay, so in this lab, I've given giving you some kind of rough examples of how this works out. In part one, you're going to explore valence bond theory. And basically, that's just going to be more Lewis structures, applying Vesper, and now throwing in the hybridization, which I'm hoping isn't too crazy. In part two, you're going to explore some molecular orbital theory diagrams. So you're going to write out some different structures and go through like how many sigmas, how many pi's, do they exist, stuff like that. And then finally, in part three, you're going to compare some structures in both valence bond and molecular orbital theory. And it's kind of a cool part. Most of the time, the information from valence bond and molecular orbital theory should be the same, but there are some exceptions, so just FYI. If you follow these rules and stuff, you've totally got this. I think you'll find that after a little bit of work, you'll have this down pretty well. So anyway, rooting for you, okay? If you do have any questions on anything, please let me know. You can email me, talk to the Learning Success Center, the Avid Center, no problem at all. Okay, that's it for the Chemistry 221 video introduction to the Valence Bond and Molecular Orbitals lab. I hope this has been helpful. If you have questions while you're completing this lab, please reach out to me or reach out to the LSC/Avid Center, which is located above the library. You can get help from them on this kind of stuff too, and don't feel like you have to do this all by yourself, okay? All right, I hope you're having a great day. Thanks for being here, and good luck on your lab.